Hello students, today we start the geometrical meaning of derivative. In previous lecture, we have studied the theorem of composite function and examples on that. In, in this lecture, we see the geometrical meaning of derivative. See here, consider a point P on the curve f of x. See the diagram, the point P on this curve. The curve is y is equal to f of x, and on this curve the point P is a f of a. Let point Q be another point on the curve, a little to the right of P. This point Q is little bit to the right of point P, means some small distance between point P and point Q in the right side of the point P. That means to the right of x is equal to a, to the right of x is equal to a, with a value increased by a small real number h. Therefore, the distance between these two vertical lines is h. Therefore, the coordinates of Q are a plus h, f of a plus h. Now, we can calculate the slope of second line PQ. Here, in this slope of the secant line connecting the point P, f of a, point P is a f of a, and point Q a plus h and f of a plus h. By using the formula for slope, the slope of the second PQ is f of a plus h minus f of a upon a plus h minus a. This is f of a plus h minus f of a upon h. We use the formula for two-point form in this slope. See, the slope of secant PQ is y2 minus y1 upon x2 minus x1. Hence, f of a plus h minus f of a upon a plus h minus a. This is f of a plus h minus f of a upon h. This is the formula for slope of secant PQ. Suppose we take h smaller and smaller than a plus h. We approaches to a as h gets closer to 0. Q will approaches P, that is as h tends to 0. The secant converges to the tangent P. That means the point Q is approaches to the point P, or point Q is closer and closer to point P. That is, h is not 0, but h tends to 0. The second convergence to the tangent at P. We can find the slope of tangent by taking limit as q tends to p of slope of secant PQ. Here, limit at h tends to 0, f of a plus h minus f of a upon h. This is f dash of a. We get slope of tangent at P is f dash of a. Thus, the derivative of the function y is equal to f of x at any point P x1 y1 is the slope of the tangent at the point on the curve. Now we see the example on that curve. If y is equal to x square plus 3x plus 2, then slope of the tangent at 2, 3 is given by slope m is dy by dx at point 2, 3, and take derivative of x square plus 3x plus 2 at point 2, 3. We get the derivative of x square is 2x and the derivative of 3x is 3, and we find the value of dy by dx at x is equal to 2 or at x is equal to 2, 3. That is dy by dx is equal to 7. Just we take here in the term of 2x plus 3, put the value of x is 2. Then we get the slope m is 7. See the diagram. This is curve, roughly curve of y is equal to x square plus 3x plus 2. This is a rough sketch of the given curve, and this is the tangent at point 2, 3, and its slope can be obtained by using derivative. This is the tangent of the curve at point 2, 3, and its slope can be obtained by using the derivative. Now next point is derivative of inverse function. We know that if y is equal to f of x is a 1, 1 and onto function, then x is equal to f of x, f inverse of x exists. If f inverse of y is differentiable, then we can find the derivative. In this section, let us discuss the derivative of some inverse function and the derivative of inverse trigonometric function. Here, our function f of x is a 1, 1 and onto function. Then x is equal to f inverse of y exists. If f inverse of y is differentiable, then we can find the derivative of the function. We see the example on that. Consider f of x is equal to 2x minus 2. Let f inverse of x is equal to g of x. Our given function f of x is 2x minus 2, and inverse of this function f inverse is g of x, and g of x is x plus 2 by 2. Their derivative are f dash of x is equal to 2 and g dash of x is equal to 1 by 2. We observe that f dash of x and g dash of x are reciprocals of each other. That means f dash of x multiplied by g dash of x is equal to 1. Now we are calculating the multiplication of these two derivatives, we get 1. We see the theorem. If y is equal to f of x, where differentiable function of x, its inverse function x is equal to f inverse of y exists, then dy by dx is equal to 1 upon dx by dy. Here provided dx by dy is not equal to 0. Why dx by dy is not equal to 0? Because in this term dx by dy is equal to 0, we can't find out this derivative. Hence our denominator dx by dy is not equal to 0. Now proof of this theorem is, let there be a small increment in the value of x, set delta x. Then correspondingly there will be a increment in the value of y, say delta y. As delta x and delta y are small increments. Delta x is not equal to 0 and delta y also not equal to 0. We have delta x by delta y into delta y by delta x is equal to 0. Now here delta y by delta x is equal to 1 upon dx by dy. Just we transfer this delta x by delta y to the right side of equal sign 1 upon delta x by delta y. Now we take the limit as delta x tends to 0 on both sides. We get limit delta y by delta x at delta x tends to 0 is equal to limit of 1 upon delta x by delta y at delta x tends to 0. And these are in the Leibniz notation. As limit delta x tends to 0, delta y also tends to 0. We see the proof of this condition delta x tends to 0 as delta y tends to 0 in the previous lecture. Therefore, limit of delta y by delta x at delta x tends to 0 is limit of 1 upon delta x by delta y at delta x tends to 0. Now separate the limit. Here 1 upon limit delta x by delta y at delta y tends to 0. We change here delta x tends to 0 as delta y tends to 0. And we use the differentiable function as y is differentiable function of x. Limit of delta y by delta x at delta x tends to 0 exists, hence, and which is dy by dx. Therefore, limit of the right side of equation is also exists, which is dy by dx is equal to 1 upon dx by dy. Now, see the example on this theorem. First example is find the derivative of the function y is equal to f of x using the derivative of the inverse function x is equal to f inverse of y in the following function. Here function y is log x. We first to find the inverse of this function of y, and y function is f of x, that means we x in terms of y as y is equal to log of x. To find inverse function of y, how it is? We express x in the form of y as y is equal to log of x, then x is equal to e raised to y. This is f inverse of y. See here properly. This is the definition of logarithm. These functions are inverse function of each other. Now we will find the derivative of these two functions and verify that their product is 1. Verify these two functions and their product is 1. Now we calculate dy by dx is 1 upon dx by dy. Now here 1 upon derivative of e raised to y is e raised to y, 1 upon e raised to y, and this is the 1 upon e raised to log x. What is the value of this? E raised to log of x is 1 upon x. Hence, they are the reciprocal of each other. Now we see the next example. Here function y is under root 1 plus root x. We first find out the inverse of the function y. Function y is f of x. That means x in the terms of y. Now y is equal to under root x1 plus under root x. To find, take the square on the both sides. We get y square is equal to 1 plus under root x. That means under root x is y square minus 1. Therefore, x is f inverse of y, and which is y square minus 1 its square. Again we take the derivative of this function. Dy by dx is 1 upon dx by dy. Therefore, 1 upon, to calculate the derivative of this function, as x is equal to y square minus 1 bracket square, and what is the derivative of this function is 2 times y square minus 1 into derivative of y square minus 1 dy by dx. It is 2 times y square minus 1 and derivative of y square minus 1 is 2y. Now to multiply, 2 into 2 is 4 and value of y is 1 plus root x, and y square plus 1 in bracket term is under root 1 plus root x its square minus 1. This is 1 upon 4 times under root 1 plus root x into in bracket 1 plus root x minus 1. 1 we get cancelled. The answer is 1 upon 4 root x into under root 1 plus root x. This is the dy by dx. Now next question is, find the derivative of the function y is equal to 2x cube minus 6 and calculate it. Value at x is equal to minus 2. Now see here, the given function is y is equal to 2x cube minus 6x. Now differentiate this function with respect to x. We get dy by dx is equal to, take derivative of this function, 2x cube minus 6x. The derivative of 2x cube is 6x square and the derivative of 6x is 6. Hence dy by dx is 6x square minus 6. Take here 6 common. 6 into in bracket x square minus 1. We know that the dx by dy is equal to 1 upon dy by dx. Therefore, dx by dy is equal to 1 upon 6 times x square minus 1. We just put the value of dy by dx in this term. Then at x is equal to minus 2, we get function y is 2 into minus 2 raised to 3. Minus 6 into minus 2 is minus 16 plus 12 is equal to minus 4. The value of y is minus 4, and at dx by dy at y is equal to minus 4, then we calculate dy by dx at x is equal to minus 2. Hence dx by dy at y is equal to minus 4 is 1 upon dy by dx at x is equal to minus 2. This is equal to 1 upon 6 times minus 2 raised to 2 minus 1, and calculating this term we get 1 upon 18. This is the slope. Dx by dy at y is equal to minus 4, and this is the slope of the function. Now students, we stop here and you solve the examples on this theorem. Try to solve the examples. Okay, thank you.